In this video, we are going to cover acid chlorides or acid halides, and we're going to talk about how to prepare this type of carboxylic acid derivative, but we'll also talk about some reactions we can perform with acid chlorides so that we have a few more tools in our tool belt for synthesis problems. Okay, so let's start with the preparation of acid chlorides. So again, we're starting with a carboxylic acid because remember, an acid chloride is a derivative of a carboxylic acid. Now, what we're going to use to turn our carboxylic acid into an acid halide is thionyl chloride. So you might remember this from previous chapters. Previously, we said that thionyl chloride will convert an alcohol group into a chlorine. So the same thing will happen here. Now, we also end up producing sulfur dioxide gas and hydrochloric acid. So those are some byproducts of this reaction. Sulfur dioxide will just bubble away into the atmosphere. Hydrochloric acid could pose a potential issue if there are other functional groups present on our molecule that are acid sensitive, but we'll talk about how we can remove hydrochloric acid later. But first, let's look at the mechanism for this reaction. All right, so we're starting with, again, that carboxylic acid. And we're going to react this with thionyl chloride, which looks like that. So we have a sulfur in the middle. It has a double bond to oxygen and two single bonds to two chlorines. Now, the oxygen that's in our alcohol group on the carboxylic acid, it's actually going to move one of its lone pairs over to create a double bond. That's going to move pi electrons up to the other oxygen. And now, because that oxygen will be negatively charged, it is going to then attack the sulfur atom in thionyl chloride. So our carboxylic acid is acting as a nucleophile. Now, when that oxygen attacks sulfur, we're also going to move electrons up to the oxygen on sulfur. So a lot happens just in that first step. So now we have formed an intermediate It can be tough to keep track of all of these different atoms and the oxygen atoms in particular. So what I'll do is I will highlight these oxygens so you can kind of keep track of which one is which. Okay, so we've got our blue oxygen, our yellow oxygen, and a purple oxygen. All right, so what's going to happen next? Well, that purple oxygen is negatively charged, and we have some good leaving groups on sulfur, those chlorine atoms. So we can move one of the lone pairs on the purple oxygen down, and one of the chlorine atoms will leave. So now we have a double bond between sulfur and that purple oxygen. Okay, now we also have that leaving group, that chloride ion that's hanging around. Although here, let me just highlight our oxygens really quickly. So that chloride ion can act as a nucleophile and attack our carbonyl carbon. Now, when we do that, pi electrons are going to move over to the blue oxygen. So now we have a tetrahedral intermediate. So on the bottom we have our alkyl group and an alcohol group. On the top we have our chloride, and we also have oxygen bonded to sulfur. And then let's just highlight our oxygens again, keep track of which one's which. Okay, so in the next step, the blue oxygen is going to donate or move its electrons over to create a double bond. And that has to kick out a leaving group. Now, the yellow oxygen attached to sulfur, that's actually a really good leaving group, that whole part of the molecule with sulfur bonded to two oxygens and a chlorine. So we're just going to kick that group out and give electrons to the yellow oxygen. And now we have recreated our carbonyl group. Although this time, the oxygen that's in the carbonyl group is our blue oxygen. So I just kind of rotated the molecule a bit. We've also produced, oh, I forgot one step up above, I apologize. So we're actually going to move electrons over to make a double bond between the yellow oxygen and sulfur, and then chlorine's going to leave. I was thinking too far ahead, I missed that step. So now one of our other products for this step is sulfur dioxide. And we've got our yellow oxygen on one side and the purple oxygen on the other side. And then we've also produced a chloride ion. Now the chloride ion can act as a base here. It's not a great base, but it can act as a base. And it can grab onto the hydrogen on our blue oxygen. We'll leave electrons behind and neutralize the blue oxygen. And now we have our acid chloride. We have sulfur dioxide gas, which will just bubble away, and hydrochloric acid. So this mechanism is a bit more complex. Remember that you're always trying to identify your nucleophile and your electrophile. And typically, these types of mechanisms involve leaving groups, proton transfers, etc. So eventually we start to see a bit of a pattern, but it is a bit overwhelming at first. Let's look at a reaction that our acid chloride could be used for after we've prepared it. So here we prepared our acid chloride, and then maybe we want to turn it back into a carboxylic acid. I don't know why we would want to do that, but maybe we decided, you know what, I don't want the acid chloride, I want the carboxylic acid after all. So one thing we can do is hydrolysis. So we're just going to react that acid chloride with water. And the acid chloride is going to be our strong electrophile because of that carbonyl carbon. Water is our weak nucleophile. So water is going to attack the carbonyl carbon, which moves electrons up to oxygen. We get our tetrahedral intermediate. We've got chlorine on there, our alkyl group, and now we have our water molecule attached. So now in this next step, the oxygen that is negatively charged will donate or move its electrons down to create a double bond again, and that's going to kick out chlorine. So now we've reformed that carbonyl group, but we still have our water group that's attached. So the chloride ion that we just kicked out can grab one of the protons, and that's going to now neutralize our positively charged oxygen. So now we have created or recreated maybe our carboxylic acid. And we've also produced hydrochloric acid. Now, again, we could turn that carboxylic acid back into an acid chloride by adding thionyl chloride. So maybe you actually have some acid chloride in the lab and you need a carboxylic acid. This is one way that you could turn that acid chloride into a carboxylic acid. Now, I mentioned earlier that hydrochloric acid, which is a byproduct, can be a problem if you have acid-sensitive groups on the rest of your molecule. So one way you can get rid of hydrochloric acid is by using pyridine. And we've talked about pyridine before. Let's see, there we go. So pyridine is a base and it won't react with that carbonyl group on our carboxylic acid, which is good, but it will react with hydrochloric acid and remove a proton from it. So that way the acid won't actually react with anything else. So this is a base that does not react with CO. Oh, I'm running out of room, but removes HCl. Okay, let's look at another reaction that we could perform with an acid chloride. This reaction is called alcoholysis. So in this reaction, we're starting again with our acid chloride. And you might have already guessed, we're going to add alcohol. And I'm just going to highlight the alkyl group on the alcohol in green, just so we can tell it apart from the other alkyl group on our acid chloride. All right, so we are going to need pyridine in this reaction as well, because one of our byproducts will be hydrochloric acid again. But what we end up forming is an ester. Now, this mechanism is similar to hydrolysis, so we're not going to go through the whole mechanism for alcoholysis, but Again, this has a similar mechanism to hydrolysis, which we just saw on the last slide. Now, our last set of reactions that we'll talk about in this lecture, they're called aminolysis. So that's where we're going to create amides. Now, remember there are 3 different types of amides. We have primary, secondary, and tertiary amides, and it really just depends on how many alkyl groups are bonded to nitrogen. So let's again start with our acid chloride, and this time we're going to add ammonia, and we're going to add that in excess. So when we do that, the nitrogen is going to replace the chlorine on our acid halide, and we end up with an amide. So this would be a primary amide. Now you might be wondering, do we need pyridine for this reaction? Because it looks like we would also produce hydrochloric acid, just kind of looking at the atoms and adding them up on each side. So luckily for us, ammonia is a good enough base that it will remove hydrochloric acid as it forms, which is why we need excess ammonia. So we don't have to add pyridine for this reaction. However, this is actually an older reaction that's not super efficient. So let's just make a note that this is an older reaction, not very efficient. Which just means it might not work very well, so you might not see as much, or you might not get your product as easily. Okay, what if we want to create a secondary amide? Well, we just have to change our amine group. So instead of using ammonia, we're going to use a nitrogen that's bonded to an alkyl group. And again, we're going to use excess. All right, so we end up forming a secondary amide there. And then you can probably guess that if we want to form a tertiary amide, we add a nitrogen group that's bonded to 2 alkyls, or 2 alkyl groups. Oops, I drew too many hydrogens. There'd only be 1. All right, so now the nitrogen in the amide product has 2 alkyl groups attached. Now this mechanism is also very similar to hydrolysis. Oh, running out of room as usual. Okay, so I think we'll stop there today. So far we have learned how to prepare acid chlorides, which is one of the derivatives for carboxylic acids. So we just use thionyl chloride. We also learned the mechanism for that reaction. We learned that once we have an acid chloride, we could turn that into a carboxylic acid using hydrolysis. And then we looked at the mechanism for that. We also saw how to turn an acid chloride into an ester by adding an alcohol. And this mechanism was similar to the hydrolysis mechanism. And then we also saw how to create amides, primary, secondary, and tertiary amides from acid chlorides. And again, this mechanism was also similar to the hydrolysis mechanism. So in the next video, we're going to look at reduction reactions with acid chlorides. We'll also look at some example synthesis problems. And then we're going to cover some carbon-based nucleophiles like Grignard reagents, for instance. And then we'll just kind of summarize all of the reactions we've learned for acid chlorides. All right, so I will see you in the next video.